Hello, I want to talk a bit about scientific publications and how to read them. First of all, I hope everyone has followed the steps I indicated, the communications, the subscriptions that provide the resources. This is the UC Berkeley course page for the fall, where resources will be uploaded each week, and we have the 2 recordings. In addition to the slides used in the talk, we also have 2 reading links for the papers on DeepSeek and Kimi K2. I had shared this link for DeepSeek, which is for DeepSeek R1. This actually garnered a lot of interest due to its application of reinforcement learning on the base model of DeepSeek V3. However, the one they found most relevant was the base model that came out. In fact, it was released on February 18th instead of January 22. I think it's worth reading both. This one is more impactful regarding the model they released for DeepSeek R1, but it provides a foundation on how they trained the base model, which is relevant to the topics of the first presentation. The other paper is Kimi K2, and before diving into the papers, I want to give an overview of what scientific publications are and their role in our learning process and in the industry in general. I will try to level the playing field. I will cover aspects from basic to more advanced simultaneously, so don't worry if you don't understand everything right away. There will be opportunities later to use other resources that will help you understand more deeply the more complex or less familiar topics. First, let me tell you that there are similarities and differences between science and engineering. Here, we are actually looking at both when we study artificial intelligence. Science is the discovery of new knowledge, and engineering is the application of science to use cases or the development of tools. The scientific method is a process through which new knowledge is discovered. Many of you are already familiar with it. It starts with a hypothesis, which is an idea about how things might work, something that hasn't been previously established, and the design of an experiment that can either confirm or reject that hypothesis. Then there's the experimentation part, which involves carrying out the designed experiment and the results, which would be the observations and findings, and then a discussion on whether the hypothesis is accepted or rejected based on the evidence. Finally, the conclusion, which includes the implications for the future. We can also see this structure in engineering publications, or those that combine science, novel knowledge, and new algorithms with engineering in their implementation in new models and tools. First, I want to comment on the importance of reproducibility in open science. It is crucial to be able to reproduce the results of other scientists from different laboratories to ensure that their findings are valid and not just something they can magically create in their lab, but rather something that can contribute to universal knowledge and development. So, reproducibility and leveraging prior knowledge are fundamental in science and engineering. This, therefore, highlights the importance of open models in the field of AI. It's very interesting that they have guests from these big companies that primarily, although they are already changing this, release proprietary closed models. OpenAI has already started releasing its open model. Google also has Gemma. Microsoft has also released some open models. They see where things are headed and recognize the value of open science. However, the cutting-edge models from these proprietary commercial labs are closely guarded secrets. To discourage or not empower their competition, they don't freely share their latest advancements. Instead, they release Grok 2, or a limited version of a model like GPT-OSS, which doesn't compare to GPT-5. This way, they can participate in the scientific community and contribute valuable things while maintaining their competitive edge. But what happens when there's a guest from a high-profile company is that people want to ask about their company. Tell me the secrets. Tell me about your organization. What can you share? However, since these things are protected, the guest clearly said, "Nice try, but I can't talk about that." I'm going to talk about DeepSeek, I'm going to talk about Kimi K2, I'm going to talk about open models, things that make me think it would be good at some point to invite people from those labs to talk about those models, the people who built them, even though commercial labs are also studying these models because it's part of the industry, studying those publications. So I want to share that as context so you understand. Speaking about the structure of a scientific publication, you'll see that there's a parallel with the scientific method I mentioned. It starts first with the abstract. In fact, when you search on arXiv, you can find the page that has the abstract, and this page here has abs in the URL. It has the authors. you can go to the author's page to see their other publications or those of the organization. This way, you can cross-reference the publications of that author. For those who are not familiar with arXiv, it is the main resource in the scientific community, mainly in artificial intelligence, information sciences, and many other sciences. This is considered a preprint archive, which is where the name comes from. This X is a Greek letter chi, so it's a play on words that they call archive. Preprint means it hasn't yet been published in a peer-reviewed publication, which is reviewed by industry colleagues and goes through a very strict review and grading process before appearing in a prestigious publication, such as a conference publication like ICML, ICLR, or NeurIPS, etc. So this allows publications to reach the public more quickly because the peer review process and then getting something to a conference and published can be very time-consuming, taking 6 months, 9 months. Meanwhile, the industry keeps advancing. That's why its profile has risen significantly. From systems like this, and this one has been highlighted as the authoritative source that allows people to publish their findings more promptly, enabling the world to benefit from that knowledge without waiting for a 6 or 9 month cycle for an official publication. On the abstract page of arXiv, you can see the summary, the abstract. Sometimes they might share a URL to a resource like a GitHub or Hugging Face where the models are available. Here you can find extensive information, not just about the theory, but also about what they are publishing, the evaluation metrics, and all that. Often, this information is present in the README itself, but you can also go to a resource like, oh, look here, you can download it here, the links are here. Here it is on Hugging Face. So you can then go to Hugging Face and see the model card, which is the card where the model is present and contains much of the same information as the README. Perhaps it's identical, but they also have this other tab called Files and Versions, and this is where you can download these safe tensors files. You don't do it manually, you do it with the Hugging Face CLI tool, which is part of the Hugging Face Transformers library, as it has become the standard. There is also an alternative to Hugging Face in China called ModelScope, which sometimes has things that come out of China before they appear on Hugging Face. I'm deviating from the script, but I wanted to show you a bit about what the models are, how they can be downloaded, how they are available, and the type of resources shared as part of a scientific publication. This plays a significant role in the reproducibility of open science, even though it's not a completely open model because they don't share the training data or the training pipeline they used. They do share the model weights. This is very important for 2 reasons. First, people can run the model and verify the evaluations they did with open benchmarks. On the other hand, inference service providers can serve that model as part of their APIs. This way, you can use the model without having to run it locally on a GPU or a GPU cluster. Depending on the size of the model, it might be beyond the reach of most people. So one has to rely on providers that serve the model. For that, it's necessary for the weights to be available. All right. The structure of the abstract page on arXiv, which is an entry point where one can view the publication as a PDF. There is also something labeled as experimental, which is viewing it as HTML. It has a bit more navigation. Some things work well, some things not so much. You can experiment to see which one works better for you, which one you prefer in dark mode or light mode, etc. But mainly what is used for the distribution of a paper is a PDF, rendered using LaTeX. At some point, we can talk about how to generate a paper like this under the structures and standards required by the publication. We can do that exercise. All right, so as I was saying, the structure of a scientific publication starts with the abstract and what I call a cover image, which is something eye-catching. Each of the benchmarks here highlights that DeepSeek, an open model, is better than other commercial models or on par with OpenAI O1. This is what made the world take notice. It opened eyes to the fact that open models and Chinese models, which have a significant overlap, are on par and in some cases surpassing Western commercial models in certain benchmarks. So that's why it created the DeepSeek moment that has been talked about a lot. The cover image can convey the importance with some benchmarks, so it grabs your attention and it's like the headline, it's what makes you want to take the time to read the rest of the article. It explains the impact it has and the relevance beyond that. In some cases, we have a table of contents, which is very useful. The introduction talks about the context, the background, and an approach which would be like the implementation methodology, speaking of engineering or experimental design, speaking of science, which is how they are going to do things to address, let's say, the motivation that could be part of the introduction. What is the problem? What challenges do they want to overcome? Why are they doing this work? What do they hope to achieve? So this is like the what and the why, and this is the how they do it. After the methodology, there are the results, which would be the evaluations, the benchmarks, how well it turned out, and a discussion that would basically be whether the hypothesis was accepted or rejected, speaking in terms of the scientific method. They show the results produced based on this experience. This way, one can understand the impact and relevance of what was being highlighted with the initial benchmarks. Finally, there is a conclusion, and beyond the discussion, the conclusion addresses the future impact and implications. The implications for the future, for the industry, for a field, for certain technology, for a particular approach. This is where one can start to speculate about the impact of this paper or the next steps for future work. It can also be a call to action for the community to collaborate in exploring certain topics more deeply. The conclusion can also discuss limitations and, as I mentioned, future work. Finally, one can see contributions or references, which is very important when going beyond a paper, especially if one is reading a publication known as a review paper. We can look at those next, as they include many references from the field. So, as I mentioned, it's very good to follow the structure so you don't feel so lost when reading so many pages. In this case, we looked at 16 pages. I'm going to show the papers now, but I won't go into very deep detail. Later, we can analyze with additional resources. I also want to familiarize myself more with the material. I want you to explore on your own and get used to navigating the information overload, to understand how to extract something from so many words, and to realize that understanding comes in iterations, with depth increasing each time you revisit the paper and read it in a different, deeper way. Understanding something you learned elsewhere, or having the experience of analyzing something. So don't try to understand everything at first glance. Understand that it's something you do by revisiting the paper multiple times. This is the DeepSeek R1 paper, as I mentioned. It has the sections we saw at the beginning, talks about DeepSeek R1 0, which is the base model with reinforcement learning. They discuss the algorithm they used, how they created the reward model, the training template, performance, the evolution process, the breakthrough moment when they achieved reasoning, and then the limitations they found with this, which they ended up naming DeepSeek R1 0. They then addressed these limitations with what they call a cold start, which helped make the reinforcement process more effective. They use something called rejection sampling, which we can look into more deeply. Basically, it's a way to curate the data used for training, and supervised fine-tuning, which is one of the fundamental principles we can also explore for model training. Finally, distillation, which is how they applied this model with smaller models, using the DeepSeek R1 model as the teacher and the other models as students to give them the ability to reason and think. So all of that is in this section after the introduction, the approach. We can see the mathematical descriptions, comparisons of different benchmarks, training curves, and experiment details. They then discuss many benchmarks with their references, how they used prompts to evaluate what the baselines were, who they compared against, how they set up the evaluation, and the concept of pass at 1 compared to pass at k, which is important to look at later. Talking about reliability, it's one thing for it to work as a pre-recorded demo 1 out of 10 times, and another for it to work in production 9 out of 10 or 10 out of 10 times. So that's something interesting to look at. Then, evaluation tables. Something very common if you haven't seen this type of table is that they bold the highest number, so you can easily scan with your eyes all the rows that are in bold. For DeepSeek R1, these are the rows where that benchmark had the highest score. This model, DeepSeek R1, compared to the other models they used for comparison. In some cases, Cloud 3.5 Sonnet or OpenAI O1 scored higher, but you can see the highest score was achieved by DeepSeek R1. So get used to being able to scan the tables and look at the bold numbers for reference, since there are so many benchmarks in different areas. It's good to get multiple benchmarks per area and understand that performance will vary depending on the benchmark. No single benchmark is authoritative. You need to look at the complete picture of all the benchmarks. This way, you can quickly scan, and perhaps it would be good to show this graphically, but you can start to see patterns with your eyes just by looking at the numbers and tables, greatly aided by the bold text. So keep that in mind when you're looking at these types of tables. Finally, as I mentioned in the discussion, talking about distillation compared to reinforcement learning when applied to different base models. And they talk about the reward process model and Monte Carlo tree search, which is an interesting methodology to explore various possibilities. I won't go into much detail on this now, but it's a way to do something like inference-time scaling, though very costly and not yet proven to be viable. However, theoretically, it's interesting to explore a tree of options and thus find the best option to delve deeper into processing. Finally, as I mentioned, the conclusion, the limitations, and the future work discussing various aspects there, and the references for future in-depth exploration, it's important to see the references to understand the prior work they mention. When you start looking up all those papers, it usually amounts to dozens or even hundreds of references. In this case, it's a moderate amount. When conducting deep research on an article, you end up looking at the publications in the reference section to go further. So keep that in mind for the future when you've thoroughly understood a paper and want to do related work. It might help to visit the publications they refer to in this last section. All right, let's move on to the paper that was linked here as the first reading, which is DeepSeek V3, the one that came out later, which is the base model on which they did the reinforcement learning to produce R1. Here they talk about multi-head latent attention, MLA, and the MOE architecture that were validated in DeepSeek V2, so these things are not new. They have done them before, but here they achieve new milestones in terms of performance and how it compares to the previous version. You can see the dark blue is V3, the light blue is V2, and you can see a very significant improvement. It also compares against other open models, even commercial models like GPT-4o and Cloud 3.5 Sonnet. As you can see, they are on par, or in many cases, better than those commercial models, or almost as good. So this also opened many eyes. What else can I tell you about this paper? Looking at the table of contents, it has a slightly different structure, not quite in line with the scientific method I mentioned earlier, but after the introduction, they talk about the multi-head latent attention architecture, MOE, infrastructures, and then about training, inference, and deployment with hardware suggestions. Here they discuss pre-training, which was a big topic of the talk, what pre-training is, what post-training is. They talk about post-training here, so this paper is more relevant than the one I initially shared for learning those concepts of model training, the stages of model training, and the elements involved. The conclusion and appendices cover these ablation studies. I want to talk about ablation studies. This is an important part to understand for a scientific publication and for a tool that comes out, because this mainly helps to attribute causality to some component of a complex system. What is an ablation study? The etymology of ablation is from the late Latin ablatio, which means the action of removing or separating. This is what an ablation study seeks to do: remove things and see what happens. This way, you can see if removing that thing still works just as well or not. Thus, you can attribute that out of the 30 things they did here. This particular thing has such an effect because they did an experiment where they removed that thing. This way, they can attribute an element of causality to those components through perturbation. For example, here they have something called multi-token prediction, MTP. So they trained two models, one small and one large, and they made a base model and a model with MTP, base model, a model with MTP. Again, as I mentioned, the bold text. Here there are some ties or some occasions where there is some improvement in the original version, so it's not always something that might have statistical power or is 100% reliable. But you can see that most of the time, according to the benchmark, the multi-token prediction component had a positive contributive effect that improved the score. So you can see, they did this, but did it really matter? According to this, it did matter, because they did an ablation study where they compared without and with and saw the difference between the two things. When you are creating something and saying that you did some important things, it is very important, if you want it to be accepted in a peer-reviewed publication, that you do ablation studies to be able to demonstrate that the things you say contributed really did contribute. Also, the same with this thing they call auxiliary loss free balancing strategy, with and without auxiliary loss. So here the baseline is also a small one and a large one based on auxiliary loss and without auxiliary loss, and you can see by scanning the bold text, without having to imagine the size of the bars, that there is a general superiority in using this version over the ablation where they removed it. This is something important to keep in mind. What is an ablation study? This paper is longer, as you can see. Instead of 16 pages, it goes up to 35, so it might take you twice as long or more to delve into it, but I recommend you look at those sections, at least to the level you can understand the architecture of these things. I'm going to show you something that helps a lot with that, and what the infrastructure is, and how it integrates with this, which involves pre-training and post-training. So that will be a good foundation to understand at some level. You don't have to understand all the details, but try to extract some information there. Here they talk about GRPO, Group Relative Policy Optimization, which is the algorithm they used for reinforcement learning. We can talk in depth about RL algorithms, and it's something I would do later. I even encouraged you to follow me on different platforms. Yesterday, someone asked if there were any publications after GRPO that are worthwhile instead of just hype, and I shared 2 relevant ones. If at some point we want to delve deeper, not all the topics have been covered here yet, but at some point there might be an emphasis on reinforcement learning. It will be a good opportunity to look at alternatives to GRPO, like DAPO or GSPO, or to examine GRPO and DPO, which stands for Direct Preference Optimization, and understand the differences between these algorithms and their implications. I think this gives you a foundation on this DeepSeek V3 paper. Finally, we have the Kimi K2 paper. Again, the abstract here talks about several things, including the introduction of a new optimizer. Optimizers are crucial for optimizing parameters in the learning process. The Atom optimizer is commonly used, but there have been significant advancements in this field. They have an improvement over an optimizer called Muon, which was shown to be unstable. So, they present the Muon clip, which adds a process to stabilize it. There are important aspects here for agent-based AI, making this model work well as an agent for tasks like tool execution and following instructions. They discuss the benchmarks and always include a cover image showing how it fits into the ecosystem, demonstrating that it is almost as good as the most expensive and powerful model from Claude 4 Opus, better than several other models, including the one released by Qwen 3.235, and better than GPT 4.1. They don't compare it against O3, but it shows that this is a very powerful and interesting model. This was published in July, and they released a recent update on September 5th, which I talked about in the latest episode of the podcast I just uploaded. It's a lab supported by Alibaba. Despite Alibaba releasing Qwen, they also support Kimi. It's a small and very innovative lab. On the same day that DeepSeek R1 was released, Kimi K1.5 came out. It wasn't completely open. I had an invitation to tinker with it, but almost no one knew about this model, perhaps because it wasn't fully available, but it was very interesting academically. In fact, I learned about that model in a previous class. It should be the one from spring. You can see the previous classes of this MOOC here, and you can see all the slides and the talks. So, in one of these talks, I saw it should be one from January when Kimi K1.5 had just come out, besides DeepSeek R1. So, Kimi is a very interesting lab and something important to keep an eye on. As you can see here, straight to the point, there's no table of contents, so it's a bit harder to navigate unless you notice that the PDFs have an internal structure based on these headers. Depending on the client or reader you have, you might have that navigable table of contents, which is very useful for orientation. I always suggest looking at the table of contents first before diving in. It's like seeing the architecture of a system before the lines of code. This way, you can orient your mental concept much better before diving in. Understand? Look, they just talked about pre-training here, about Muon clip, the data, the architecture, the training infrastructure. The training recipe is somewhat open regarding that, and post-training, SFT, RL, the RL infrastructure. So you can review all those concepts discussed in the MOOC talk about pre-training and post-training and these techniques as well. The evaluation, how they evaluated post-training, how they evaluated pre-training. Evaluation is important. It's a complex topic, as mentioned in that talk, and the safety evaluation of the guardrails, limitations, conclusions, and then the credits. Additional things are like appendices that are not part of. Once they come after the conclusions, they are like extra data that are not fundamental to understanding the main message they are sharing. One interesting thing about this paper was the training curve, which was literally highlighted in bold. Look at how great this training curve is, because there are training curves that have normal spikes, which means they were able to achieve a very stable process leading to a well-performing model. I'm telling you this because I'm going to show you a comparison that says this is not such an extraordinary result, but it is interesting. They have good diagrams that help you compare different aspects of the training, and honestly, it's a very well-founded and well-done paper beyond the quality of the model. One thing that was greatly appreciated and recognized was the quality of the technical report of this paper. Here again, you have the comparison tables of different proprietary and open models, and we can look at the bold text and see how Kimi K2 stands out in bold. But, well, they are comparing it against R1 only with V3, not comparing it with Qwen3 thinking. This might be the instruct. One always has to look at these comparison tables, not only for what they include, but also for what they exclude, because that makes you think critically. It's not necessarily that they are trying to hide something, but it's very common for them to try to present their model as the best in the world, and perhaps strategically exclude some comparative models. Professor John Paez from the community shared something interesting about a spiking neurons model based on neuroscience, a model that is computationally efficient. The concept is interesting, and of course, they present the comparative table, saying, look, we are better than all the others, but those other models are very old. They compare against Llama 2, I think, not even 3 or 4, and things like that. Sometimes this is due to the publication cycle. Although a publication has just come out, the previous model might have been available much earlier, or they took a long time to release the evaluations. When they started, the other model might not have been released yet. There are various reasons why this can happen, not always for disingenuous reasons, but it's something to keep an eye on. You have to keep in mind when you see these bolded tables what the counterparts are to understand exactly. Here they are comparing against Sonnet 4, and we can see in some cases, yes, Sonnet 4 is still better or Opus, but it's almost on par in several aspects, in some a bit less. However, it's a good first approach to look at the reference graphically and in tabular form. So, one has to start looking at these papers critically. My first experience reading papers was perhaps around 2008 or something like that, while taking some graduate courses in biological computer science or computational biology in systems biology. We were looking at very technical publications from people you would say are very intelligent, and a bunch of graduate students there, and I was just tagging along, young people without an academic background. However, the professor, who was very good, helped us think critically, evaluate these papers that even though they come from big labs and brilliant minds, can make mistakes, misrepresent, or hide data. So it's good to read critically, to think about what the limitations are, what possible flaws might exist beyond what is seen. It's a good invitation not to be intimidated by so much technicality and the vastness of the labs that produce this. As an amateur leaning towards professional, you can start to understand certain concepts and read critically, which is fundamental for one's development and the industry's development. So I invite you to have that kind of mindset, not just to read a paper and take everything as, wow, this is the best in the world. Because in some cases you see it, but in others, it's how they want to present it. It's a skill you develop over time, but something I encourage you to keep in mind as something to develop. All right, here I finished scrolling through the Kimi K2. You can see the references are listed here. There are 91 references. So if you plan to do an in-depth research on Kimi K2 and its references, it will be a more time-consuming and extensive task. To conclude, I want to share a resource that will help you visually understand a lot about this. You can look at architectural topics in a much more visual and accessible way. There is a scientist, I call him a scientist. He is also an engineer, a great one named Sebastian Raschka. He is a very good person and has written this book called Build a Large Language Model from Scratch, and he keeps it updated for implementing Scratch models in various cases. He provides the training weights, because one might not have the resources or data to train these things, but besides having the weights, he shows how to integrate them into an architecture. It's a very powerful and involved process that some of us might start to face. He sells this book, or the publisher sells this book. You can buy it on Amazon or many places like O'Reilly. If you have corporate support or resources, you can buy a membership on O'Reilly, which is about $300 a year. And you can read all the O'Reilly books in the world. It's money well spent if you are going to be reading technical books. $300 might be out of reach for many, and I'm not saying it's necessary, but if you have the opportunity to influence your company and tell them, look, this is a good resource that would allow us to have access to a great source of knowledge, I encourage you to do so because you will have access to an immense amount of publications and also support the authors of these books. Beyond that, there is also an open repo where he has all the code related to this. Just search for LLMs from Scratch, Sebastian Raschka, and I will share the links as well. You will find a lot of notebooks there, so you don't have to buy the book to play with the code he has, although I recommend it. Why do I mention Sebastian Raschka and his work? because recently he released this incredible resource on his blog. I'm going to subscribe and pay for his blog, but he also has a free version. I encourage you, as I mentioned, to subscribe to blogs, not just mine or those from the Center of Excellence or the UC Berkeley MOOC, but also to other sources of knowledge that will enrich your understanding and the algorithm so you can be exposed to more information. It's called the Big LLM Architecture Comparison, and here he keeps updating it with new models as they come out. It has a visual comparison of the architectures of various models, including the ones that are just now being released. The first one is the first we saw in DeepSeek V3, and R1 uses the same architecture. R1 has reinforcement learning on the model. It talks about multi-head latent attention, as I mentioned, which they highlight. It also talks about mixture of experts, which they also emphasize, and these are the things that help differentiate these models. It has this type of diagram where one can understand. Don't worry if you don't understand any of this. These are things we can study more in depth later. But the token embedding, the normalization in the attention. And here is a call out where you can see in detail how multi-head attention works. Normally, you have an input query, key, and value. Here, there is a compression of the key and value, which reduces the memory of the KV cache, something fundamental for efficient inference. And then normalization, mixture of experts, final normalization, and output layer. So that's the general architecture in very broad terms of this model. You can also see here, this is a table taken from the previous DeepSeek V2 paper, where they also discuss these different components and MLA. So, as you can see, this isn't something new, but it's something their models highlight. They talk about mixture of experts here, the difference between a dense model and an MOE model, where only certain experts are activated for each token. This doesn't save memory because you have to load all the experts into memory, but it saves a lot on GPU processing because fewer parameters are activated for each token's processing. This means you can perform fewer computations to process the token, which is very important not just when processing locally for yourself, but also if you're a server or an inference provider with 1,000 or 1,000,000 people connected. Here, computational efficiency becomes much more significant, regardless of the memory needed to load the model. It's about processing it efficiently with good tokens per second. So here they talk about the MoE layer, the resources saved, and although the model size is 171 billion parameters, only 37 billion parameters are active at each step. Beyond that, it shows a summary, talks about other models, and mentions the OLMo2 model, one of the most open models. I've commented on this several times. This organization stands out for its transparency in training data, code, and technical reports. They are making a great contribution to humanity and the industry with their work. They also collaborate with Hugging Face for training small LM, a very good collaboration. Recently, another open model, Apertus, was released, which I also mentioned in the last podcast. I hope it joins the consortium of these great labs doing good work. So one understands this is called a Pareto frontier, where you look at two factors like training and performance, and you see it's a curve, a trade-off. Sometimes it's like comparing apples to oranges, saying this compared to that when they have different parameters. But if you can see the curve, you can see something is at the tip of the curve or beyond, and thus you can understand this Pareto frontier, which highlights the relationship or proportion between two different parameters. Something important to understand when this type of diagram or publication comes out. Many technical details there about Olmo, Gemma 3. We talked about Gemma 3, which is Google's open model. We talked about Mistral, Llama 4, and when it was released. We can see comparisons with other models like Qwen 3. Here they show the dense models, which are the small ones, and the large ones, which are the mixture of experts. So here we can compare DeepSeek V3 with Qwen 3, which is a model 1/3 the size. That's why this comparison might not be very fair because it's like a different weight class, literally. Normally you want to compare models of the same weight or slightly larger to show better performance with a smaller model. This way you can demonstrate the power and efficiency of the small M3 model I mentioned earlier. Here you can see a type of Pareto frontier of model size and performance gains. This shows an interesting alternative for very small models. We're talking about 3 billion parameters, super small. That's why the name small LM. Small is a colloquialism in the AI engineering world to say small in a cute way. There's an organization called Small AI, which is very good, and I'll send you more resources related to them later. Also, this is another joke. We have rope that we saw before, and now NoP, which is no positional embeddings. Finally, we get to Kimi K2, and here it says, look at this curve, which was so stable, compare it with Olmo's, and this blue one, which is the previous version of Olmo. If you want to talk about a smooth training curve, nothing compares to this. It's out of this world. So something to recognize and appreciate about what Olmo is doing there. Finally, this is a very good comparative graph. We are seeing these two models, how we can compare DeepSeek V3, R1, or Kimi K2. This is a giant model, a billion in a trillion, 10 to the 12, 10, 12. We can compare, look, this one has more attention heads. That's the difference in the mobile layer. How many experts do they have? How many are activated at each moment? There are many similarities. Both use rope for attention. There are many similarities and some slight differences in the architecture. So, I highly recommend this resource to understand, without needing to grasp every detail, the broad, visual architecture of these different models. I'll leave you with that. Here are more models like OpenAI's OpenLab and Grok 2.5, which they released, and GLM, a very interesting model from GPU AI. They have the best AI domain, ZAI. I recommend checking out that model. There's a free chat, but also via OpenRouter, because it's a powerful model in terms of its agency power, its ability to use tools and follow instructions. They have a subscription plan that I think is $9 a month, and it's much higher usage than Cloud Code. So many people are switching from a Cloud Code subscription to the GLM 4.5 subscription and using it with Cloud Code or other editors. Highly recommended. This model just came out recently. That's why I say it keeps updating. This is from September 17th, and on September 11th, Qwen 3 Next was released. For those who don't know, it's a super sparse model because compared to the previous Qwen 3, which had like 30 or 32 billion parameters with only 3 active, I think it was 30 and measured against the 32, even though it only had 3 active. This Qwen 3 Next instead of 30 has 80, and still only has 3 active. This makes the speed brutal, the cost efficiency brutal, as I mentioned. What matters for memory is how many you have loaded, so it won't be easy for anyone to load this locally unless they have 2 GPUs or something brutal like that. But to use it via API, it's powerful, needing only 3 billion parameters, making it very fast and therefore very cheap. Keep an eye on Qwen 3 Next. It's an interesting model. And the MTP, which you remember we saw in the ablation studies of DeepSeek V3, that's why it says it has a similar architecture. So that's it. I hope this leaves you with an understanding of the structure of the scientific process of a scientific publication and how to understand a technical publication, which can be overwhelming, but you can start extracting valuable information from it.